Okay, so can anyone confirm that if they can see my slides?
Yes, sir.
Thank you. Okay, so as you know, so welcome back to the cryptography course. So we started with the the basic introduction. So now, in order to show you a couple of things, I should say that. So this was the course. So first I'm going to cover some more classical ciphers, which I have not mentioned here, but but they are kind of elementary things. It's not very difficult to understand them, but it's a good starting point. So they all come in what is known as classical cryptography. So this classical cryptography. So and then we'll discuss later on private key, public key in protocols and so on. So first I am going to focus on classical cryptography. Now before we start classical cryptography, I need to do some little bit of mathematical background. Though people who have done course in my section, probably they know this stuff, or in other sections I'm not sure in 2019 batch. But even if I'm so it's a long time, so maybe I'll just recap few things from there, so that the basic background. So if you feel that okay, this stuff, that's okay. I mean, because I'm just trying to build it from the basics. Because there may be some people who may not know this stuff. Okay. Okay. So first very interesting thing that we know is you know integer modulo m. This is, we call it as, elements are 0, 1, 2, 3, m minus 1, right? With addition modulo m and multiplication modulo m, these two operations. This whole thing is known as ring, right? Why ring? I think I'll tell you in a minute. So let us start with the very basic things. So let us take m is equal to 2. So that means, so what we are doing, we are taking all the integers, dividing it by m, and see what are the possible reminders, right? So here are total m reminders, right? So now if we do it for say m is equal to 2, so there are two possible reminders. We list it as z2, integer modulo 2, right? 0 and 1, and operations are plus 2 and multiplication of 2. So now, I think if you remember, we have done this kind of stuff earlier. 0, 1, 0, 1, addition sign, plus 2, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and what is 1 plus 1? Anyone?
0.
0. Good. This is the binary arithmetic, right? With respect to addition, we are doing. Similarly, we can make it for, multiplication of 2, 0, 1, 0, 1, 0, 0, right? Then we have 0, and 1 into 1 is 1. So other than 0, so basically we want to make sure that every element has additive inverse and multiplicative inverse. If we satisfy these two things, so all other things are anyway true, then such kind of set is known as field, right? What is a field? Where we can do all the four operations: addition, subtraction, multiplication, and division. And the well-known examples of infinite fields are field of rational numbers, field of real numbers, field of complex numbers. This we have already done earlier, right? These are all examples of infinite fields. Infinite fields. So what is a field? Field is a set of numbers where we can do all the 4 operations: addition, subtraction, multiplication, division. So Q, R, C are well-known examples of infinite fields. So now I am going to give you some idea about finite field. So this set is a field, because with respect to addition, every element has an inverse here. You see, 1 plus 1 is 0. So here, since 1 plus 1 is 0, 1 is inverse of itself. So that means 1 is equal to minus 1 here, right? This implies that 1 is equal to minus 1. So 1 is inverse of itself with respect to addition. Similarly, here 1 into 1 is equal to 1, right? Because of this result, we look at this, 1 into 1 is 1. So 1 is self-inverting with respect to multiplication. What happens if we take m is equal to 3 now? For m is equal to 3, one can make a table here again: 0, 1, 2, 0, 1, 2, 0, 1, 2, 1, 1 plus 1 is 2, 1 plus 2 is 3. Modulo 3, it will be 0. 2 plus 0 is 2, 2 plus 1 is 3. Modulo 3, it is 0. And 2 plus 2 is what? 4. Modulo 3, it is 1. So with respect to addition, similarly we can make a table with respect to multiplication. With respect to multiplication. So this is 0, 0, 0, 0, 0. 1 into 1 is 1, 1 into 2 is 2, 2 into 1 is 2, and 2 into 2 is 4, modulo 3, it is 1. So this is how the things are. Now, with respect to, you can see that 1 is a multiplicative identity, so I can identify a multiplicative identity. So I can identify the inverses. So 1 into 1 is equal to 1, and 2 into 2 is equal to 1. Okay. So that means 1 is inverse of itself and 2 is inverse of itself, right? So basically, you can say that every element has a inverse. Of course, other than 0, right? And here we have, with respect to addition, everything has an inverse of itself, because 1 plus 2 is equal to 0. So 1 and 2 are inverse of each other, right? With respect to addition, here 1 is self-inverting and 2 is self-inverting, right? Okay. So so this is a common structure, basically, about field with 3 number of elements. So this is field with 2 number of elements, this is field with 3 number of elements. We denote it by Z3, right? So now actually we go to a little bit further and take m is equal to 4. When we take m is equal to 4, we get integer modulo 4. Elements are 0, 1, 2, and 3. Operations are plus 4, and multiplication of 4. I can say that 0, 1, 2, 3, 0, 1, 2, 3. This is with respect to 4, 0, 1, 2, 3, 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, modulo 4, which is 0, 2, 2 plus 1 is 3, 2 plus 2 is 4, modulo 4, it is 0, 2 plus 3 is 5, modulo 4, this is 1, 3, 3 plus 1 is 4, which is 0, 3 plus 2 is 5, modulo 4, which is 1, 3 plus 3 is 6, modulo 4, which is 2, right? So we have this modulo operation. Similarly, we can have it for multiplication. 0, 1, 2, 3, 0, 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 2, 2 into 2 is 4, 1 to 4 it is 0, 6, this is 2, 3, 3 into 2 is 6, which is 2, 9, which is 1. Now you can see that here, with respect to addition, everything is a. So my question is, anyone can answer, is this a field? Can I do all the 4 operations here? Anyone can unmute and answer.
No, sir.
Why?
With respect to multiplication, in there is in two there no inverse in for two.
Correct. So there is no inverse for 2. You can see that because 2 into 2 is equal to 0, right? So in fact, another way to identify this is that if I identify 1, 1, so that means 1 into 1 is 1 and 3 into 3 is 1. So there are 1 is self-invertive, 3 is self-invertive, but 2 there is no inverse, right? I mean there is no 1 here. There is a problem. With respect to addition, everything is fine, right? Because we have here 1 plus 3 is equal to 0. So 1 and 3 are inverses of each other, and 2 is self-invertive with respect to addition. This is okay. All the 4 operations you can do, I mean here, of course, other than division, when you can do all the for the groups actually, and here, 2, there is no inverse for 2. So the question is, when do we say if A in Zm, integer modulo M, A inverse exists, if what happens? Can we say anything? Any idea? So first of all, let us see few things. Let us go back here. If you look at in this example, integer modulo 3, what is 1 by 2? Which is nothing but 2 inverse. What is this value? 1 by 2 is not 0.5. Remember, this is 2 inverse. What is 2 inverse here? Anybody can unmute and answer. 2, correct, because 2 into 2 is equal to 1, right, from here. So 2 inverse is 2. So 1 by 2 is equal to 2. So you remember 1 by 2 is equal to 2. 1 by 2 is not equal to 0.5. It's not equal to 0.5 as you think, right? This is something that you need to remember. 1 by 2 is equal to 2, right? So the question is, here you can see that in integer modulo 3, there is inverse for every element, right? Integer modulo 2, of course, I mean integer modulo 3 inverse of every element other than every non-zero element has an inverse. In case of integer modulo 2, every non-zero element has an inverse. But case of integer modulo 4, only 2 elements has an inverse, others do not have it. But if we go a bit further, I think we can take one more example here, and let us
Sir,
see. Yes.
one question. Is
Yes.
there anything to do with prime number here?
Yes, prime number is something you mean to say in this condition here?
No, I mean to say the inverse do exist for prime numbers because
Yeah,
2, 3.
if it is integer, if p is a prime number, like integer modulo p we consider, so
Hmm.
every non-zero element will have a inverse. But there is a reason actually. Of course, yes, true. It is true that here in this case the inverse will exist, but the condition I should mention, uh, a element in integer modulo M has an inverse, so A inverse exists if and only if GCD of A and M is 1. This is a very beautiful condition actually, right? If you take M is equal to 2, so you see that there is only one solution, right, which is 1, right? So in fact, if you take M to be prime number now, M to be P, a prime number, then you can see that this condition GCD of A comma P is 1 for every A not equal to 0 in integer modulo P. Do you agree? Every
Yes, sir.
element, non-zero element in ZP will have GCD 1. with P, right? Because elements will be 1, 2, 3 up to P minus 1, right? So they will have GCD 1 with P, right? So that means every element will have an inverse. This is a important result. So I would like to ask you, take a cup of tea or coffee in the evening and try to solve it. This is tea time problem. I leave it for you to verify that a element A in integer modulo M has inverse if and only if GCD of A and M is 1. You need to verify this. Okay, verify. How will you verify? I mean, prove it. Try to see if you can find a proof. I think I am assuming that you have done now a course on discrete mathematics. Right. So you know we have done this proof earlier, but just recall. The best way to recall is now take a cup of tea or coffee in the evening, sit down in front of a tree or something, and then just try to establish this fact, right? That an element A in ZM. Now, for example, if you can see here, in case of Z4, what happens? Right, 1 will have inverse because GCD of 1 and 4 is what? GCD of 1 and 4 is what? 1, right? GCD of 3 and 4 is what? 1. So both 1 and 3 has inverse, right? But GCD of 2 and 4 is 2, which is not equal to 1. So 2 doesn't have an inverse, right? This is a really very basic thing to observe. Okay. So this is very, very important as well. This result is very, very important. I am going to use in the cryptography this result quite often, actually, So just memorize it, and the best way to memorize is do it yourself. Just try to establish this result that in integer modulo M, an element. I'm assuming that A is non-zero, of course. A non-zero element has a inverse if and only if GCD of A and M is 1. Okay. Any question at this point? Any question at this point? You can say yes, no, nothing.
No questions.
Okay, good. Thank you. So let me go a bit further. Same thing. You can do it for integer modulo 5. We have 0, 1, 2, 3, 4, right? Integer modulo 4, and operation is plus 5 dot 5. You can see that everything. So you can make a table, right? It's easy. If I ask you what is 2 by 3, can anyone tell me what is 2 by 3 here? 2 by 3 will be 2 into 3 inverse. So inverse of
4.
3. Huh?
4.
Overall is 4. So
Yes, sir.
what is 3 inverse?
3 inverse is 2.
2. And so this is 4. Good. So now you remember this 2 by 3 is actually like this, right? Things are a little bit different in this as compared to, it's not a decimal, it is 4. 2 by 3 is 4, right? These kind of things you will encounter quite often. So I think you should have the familiarity with this kind of things. Why we are interested in these rings? Because there is a ring integer modulo 26 in which we are very much interested. Why this ring? Can anyone guess? Anyone? Please unmute and answer. Why we are interested in integer modulo 26? So I am interested when m is equal to 26.
Number of alphabets in English, 26.
Yes, number of alphabet in English is 26, and so whenever we are going to make a cipher, means there is a plain text, English text, right? We actually convert every alphabet into some integers, right? So we map it to elements of Z26, and then we develop a crypto system there. So that's why this is very, very important. And now the question is, Z26 is a ring or a field? Again, answer me.
Maybe a field because 26 is not a prime number, so
No.
it's a ring on Hopper.
Huh? Again, repeat it. I think
26 is not a prime number,
26 is not a prime number. Yes.
so it does not have an inverse. Inverses नहीं है तो field नहीं हो सकता.
Yes, this is not a field. Okay, this is a ring. Okay. So essentially, you may ask what are the properties of the ring. I now I can mention some of them. Though they are very simple, but anyway, I will mention it. So integer modulo m is a ring in general. It's a ring. So what are the properties? That if you take two elements a and b in integer modulo m, this implies that a plus b belongs to Zm. Addition is in the ring itself first. Second property, okay, if a and b are in Zm, then addition is commutative. That means a plus b is equal to b plus a. Okay, that means closed, commutative. Third property, associative. If a, b, and c are in Zm, right, this implies that a plus b plus c is same thing as a plus b plus c. Fourth property, there is a additive identity. Zero exists. There exists zero in Zm, such that for any a in Zm, we have a plus 0 is equal to 0 plus a is equal to a. Right? These are the four properties. There are a couple of more I should mention for you. Okay. Fourth, then fifth property. There is additive inverse. There exists additive inverse. Inverse for any a. For any a in Zm. Right. So additive inverse of a will be m minus a. Right. So this is same thing as m minus a plus a, which is 0 for any a in Zm. Right. Sixth, so this was additive inverse. Multiplication is closed. If a and b are in Zm, then a into b belongs to Zm. Seventh, multiplication is commutative. If a and b are in Zm, then ab is equal to ba. Everything is modulo m we are taking, right? Eighth, multiplication is associative. If a, b, and c are in Zm, then we have ab times c is equal to a times bc, right? Ninth, there exists multiplicative identity 1 in Zm. This implies that for any a in Zm, a into 1 is equal to 1 into a is equal to a. This is true. And 10th, there is distributive property, distributive property. What is distributive property? That a plus b into c is equal to ac plus bc, and a times b plus c is equal to ab plus ac. This is true for every a, b, c in Zm. So these are the 10 properties which holds actually for this ring actually. Okay. You can clearly see that multiplicative inverse I have not talked about, because if multiplicative inverse is also there, then this is a field actually, right? So which is not here in this ring case, right? This is something very, very important for you. And since we are going to look at basically integer modulo 26, which is a ring. So we should know these properties all the time. But we can always make these kind of tables. For example, Z4 is also a ring. Z4 is a ring because not every element has an inverse. Okay. So similarly, Z26, not everything has an inverse. So maybe I should ask you a question. In integer model of 26, which elements has inverse? Suppose A is a non-zero element in the
13. 13 could be the answer.
No, only 13, or there are a couple of more will not have inverse.
13 and 2.
That is there, but there will be more actually, right?
Because if I factor 26, 2 and 13 will be the prime number,
Hmm.
and when we basically see, there will be no other prime numbers other than 2 and 13. So these will not have multiplicative inverse.
Certainly, these will not have. Are there more? So again,
Prime number between 0 to 26.
verify or find. I think again this is a tea time problem now for you. It's not a difficult problem, right? Tea time problem for you. Find all the elements which has inverse. Find A, find non-zero A basically. Find non-zero A in Zm such that GCD. So basically GCD condition will come such that A inverse exists
So maybe every even number would not have inverse.
in Z26.
Sir, I think
Yeah.
that all the numbers which have
So
GCD
basically the condition will be what? If GCD of A and N is 1, inverse
1, yeah.
exists, right? Right? So you need to only find what are the A's for which this GCD is 1 from M is equal to 26, right? How many of them are there actually? See, there is another way of. Do you remember this function phi of 26? Do you remember anything? If you don't remember, I leave it to you. I will anyway come back to this function. I will come back to this function, but I am just giving you hint. Okay, this is your hint. Okay, this is known as Euler's function. Anyway, so GCD of A and M is 1. You can find out, you just list all the elements and see, so you list Z26, all the elements like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, right? Now you check which elements other than non-zero, this we can leave. Which element has GCD 1 with 26? This number, yes. 2 has GCD 1 with 26? No.
No, sir.
No. What about 3?
Yes.
Yes.
Yes. What about 4?
No.
No.
No. What about 5?
Yes.
Yes.
What about 6?
6.
No.
No.
No. What about 7?
Yes.
Yes.
What about 8?
No.
What about 9?
Yes.
What about 10?
No.
What about 11?
Yes.
12?
12.
No.
No.
13?
No.
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 14?
No.
15?
Yes.
Yes.
16?
No.
17?
Yes.
Yes.
18?
No.
19?
Yes.
20?
No.
21?
Yes.
22?
No.
23?
Yes.
24?
No.
25?
Yes.
How many of them are there? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are total 12. Right? 12 elements which have inverse in Z26. So that is it. This is a ring. Now actually from here also, if you compute 5, 2 is equal to 1 and 5, 13 is equal to 12. So your answer is 12. So what is this Euler torsion function? We will actually come to know a bit later on. Okay. Okay. Any question at this point? Any question at this point?
No, sir.
Good. Okay, so this was a little bit of about integer modulo m. We will come back to 2 or 3 more properties, such as finding inverse of a matrix. Anyone remember about the matrix?
Yes.
I think we have done in discrete math class, and after that also you might have done a course on algebraic structures for linear algebra, right? Which course you have done? Linear algebra?
Yeah, linear algebra.
Okay, so you know about matrix anyway. So we'll talk about interesting things about matrices. When we look at matrices over these kind of rings, many interesting things will happen, which you have never seen. I will show you some beautiful things, some beautiful properties. Okay. Anyway, so basically, now I am going to give you some idea. So about so basically we will look at two things in the next class. One is about solving a equation, and I think that also we have done earlier, something like ax congruent to b mod m. When we'll have this equation has a solution, these kind of problems we are going to study, and also finding inverse of a matrix over integer modulo m when a matrix A has a inverse. These kind of problems we are going to study, and they are very useful for developing ciphers. So we'll see that thing. But now I am going to focus on a couple of more finite fields. So this is basically I constructed less than infinity fields. I call it finite fields, right? Finite fields. What are the finite fields? So can we say that there is a field with one number of elements? Anybody can answer, unmute and answer. One number of elements. Is there a field with one number of elements? We know there are two number of elements, field with two number of elements, right? Which is the one? Integer modulo 2. Fine. Three number of elements. Integer modulo 3 is the answer. Four number of elements. Integer modulo 4 is the answer? No. This is not a field, as you saw. Right? Five number of elements. It is Z5. Six number of elements. Can we say Z6 is a field? Yes, please unmute and answer.
Okay.
It is not a
No,
field.
it's a ring.
Because 3 into 2 is equal to 6, which is 0. Right? So 3 and 2 are 0 divisors. Basically, it is not a field. This is a field, this is a field, Z2 is a field. What about one number of elements? Can we say that there is a field with one number of elements? Now, please unmute and answer.
No, sir.
Why one number of element cannot be a field?
Because only 0 will be there and 0 does not have any multiplier inverse.
Correct. So basically, you require at least 0 and 1, because multiplicative identity is also required, right? In the field. At least two elements. So this is not a possibility. right? So 2, 3, 4. So the question is, how do we construct field with 4 number of elements? How to construct field with 4 number of elements? Because Z4 is not a field. Yes, so now again I am just trying to see if you remember anything. Anyone can unmute and tell me how to construct. Some idea I want to listen if you remember anything or not. This was the most important thing that I taught to you, and I guess yes, anyone.
Sir, we will generate, consider for 2 and 3 alpha, and 0 and 0 1 has a field, so we can construct by that.
Okay, so some alpha you remember, very good. So let me show you the construction method, because this is a very important one. Why do we need these finite fields, as I mentioned? So modular arithmetic, which I have shown to you, the integer modulo m, is useful for classical ciphers, right? Now there are a couple of other things. For example, have you heard of AES? Have you heard of AES?
No, sir.
Advanced encryption standards. It is based on finite fields. Or elliptic curve crypto system, elliptic curve crypto system, ECC. They are based on finite fields. There are many interesting problems, you know. So basically, these things are based on finite fields. So that's why you need to have these ideas, you know, finite fields. Okay. So let me look at this construction. How do we construct complex numbers from reals? How we construct complex numbers from reals? So you remember what we do? We say that take a polynomial x squared plus 1 is equal to 0 in reals, which has no root. No root in reals, right? Then what we do? We suppose there is a root I. I is a root not in R but outside R. Outside R. Right? And we attach it to R. So basically C is nothing but R attached with I root. So this is nothing but A plus IB such that A and B are reals, right? And I square plus 1 is equal to 0. That means we say that I is equal to square root of minus 1. You remember this fact? This is how we construct field with complex numbers of elements. This is also a field. Reals, this is a field. Means you can do all the 4 operation: addition, subtraction, multiplication, division, and then we can extend it to do little bit more operations, right? Now the question is, we can do the similar thing from Z2. Z2 is integer modulo 2. We have 2 elements. It's a field. Analogous to R, we have Z2 here, and I need to construct field with 4 number of elements. I will denote it by ZF4, field with 4 number of. It is known as Galois field with 4 number of elements. So how do we construct this? Or sometimes we use the notation F4. Or yeah, so these two are the common notations. So how do we construct a field? So just like that, here we have taken equation. So if I take equation here over degree 2 equations, so equation I can take here ax square plus bx plus c is equal to 0, where a is not equal to 0 and a, b, c belongs to z2, integer modulo 2. How do we solve it? A is not equal to 0, so a will be 1, right? So the equation is x square plus bx plus c. How many equations are possible now? Anyone can unmute and answer? There are two choices for B, two choices for C, because B and C belong to Z2. 4 equations. So I can write it down, all of them. The first one is x square plus x is equal to 0. Another one will be x square plus 1 is equal to 0. Another one will be x square is equal to 0. Another one will be x square plus x plus 1 is equal to 0. Now, is this root, this equation is having any root in Z2? X square plus x equal to 0. Because if you put x equal to 0, 0 plus 0, it is satisfying, right? So 0 is a root. So this equation is not going to work. I see, remember, here I have taken an equation which has no root in R. So I need to consider a equation over Z2 which has no root in Z2 actually, right? So this equation is not going to work. What about this equation? X square plus 1 is equal to 0.
This will work
X
because
square plus 1 is equal to
under
0
root
is
of
what?
minus 1, under root of minus 1 will be there.
No,
So-
minus 1. My dear, there is no square root of minus 1. This is finite field business. This is not real or complex. So solution is either I put x equal to 0 or x equal to 1, right? If I put x equal to 0, 0 is not a root, fine. But if I put x equal to 1, 1 plus 1 is what? Z2 mein?
0.
0. 1 plus 1 is 0. So 1 is a root here, right? So this is also not going to work. Understood? What about
Yes.
x square is equal to 0? Which one is the root here? 0 or 1?
0.
0 is a root. So this is also not going to work. So only one equation is left. Now let us try. If you put x equal to 0, what happens? 0 plus 0 plus 1, which is 0, right? 1. 0 plus 0 is 1, right? So 0 is not a root. What about x equal to 1? 1 plus 1 plus 1 modulo 2, that is 1. So 1 is also not a root. So this equation is going to work. Bingo, we have found a equation which has no root over Z2. Now just like that, here we attach I attach here some root, I just put some symbol. I call it alpha. Suppose alpha is the root of this equation, which is not in Z2. So this root is not in Z2. So alpha square plus alpha plus 1 is equal to 0. So here GF4 will be A plus alpha B, such that A and B are in Z2. And what is alpha? Alpha square plus alpha plus 1 is equal to 0. Right?
You please repeat.
Yeah. So we started with equation. So we were looking for a equation over Z2 which has no root, right? So now over Z2, we tried, there are 4 equations possible of degree 2, right? So we saw that 3 equations do not have a root. Only one equation, x square plus x plus 1 is equal to 0, has a root. X square plus x plus 1 is equal to 0 has no root over Z2. So we call alpha is a root in this equation which is beyond. So just like that in the reals, we assumed I is a root of the equation x square plus 1 is equal to 0, which is not in R but outside R. Similarly, alpha is a root of x square plus x plus 1 equal to 0, not in Z2 but outside Z2, somewhere else, right? So we attach just like that a plus ib, we do a plus alpha b such that ab belongs to Z2, and this equation I square plus 1 is equal to 0 is here alpha square plus alpha plus 1 is equal to 0. Got it? Pure analogy with real to complex. How we go? Similarly, we go from Z2 to field with 4 number of elements. Now whether this is a field or not, that we will check now. Okay, now let us do some beautiful things. First of all, now you know that, so we have got this equation GF4 is equal to this set a plus alpha b such that a and b are in Z2. Okay, and alpha square plus alpha plus 1 is equal to 0. Now let me do couple of calculations for you first. What is alpha cube? Alpha cube is what? Alpha into alpha square. Do you agree? This is same thing as alpha times. Now from here, since alpha square can be written as minus alpha plus 1, do you agree? Because alpha square plus alpha plus 1 is equal to 0, so alpha square is equal to minus alpha plus 1, right? So that means now minus alpha plus 1 is same thing as alpha plus 1, because 1 plus 1 is 0 here, if you remember, right? So alpha square is nothing but alpha plus 1 is equal to alpha square plus alpha. Now alpha square plus alpha is equal to minus 1, same thing as 1 from here. So alpha square plus alpha is equal to 1. So alpha cube is equal to 1. Got me? Any question at this point? Any question at this point? Please
And how
unmute.
minus 1 plus 1 equal?
Yeah. Ask me what was the question?
How minus alpha plus 1 equal to alpha plus 1?
Because minus 1 is same thing as plus 1, right? Integer modulo 2, what is the condition? See, this here, if you look at here, all these elements, what are the elements here? I can list down 0, 1 plus 0, 1, 1 plus alpha and alpha, right? These are the roots here. These are the elements here, 0, 1 and 1 plus alpha and alpha, right? So what happens? All these coefficients you see are in Z2 only, right? All these coefficients are in Z2 only. So because of this restriction, because coefficient arithmetic remains in Z2, minus alpha is same thing as plus alpha. Do you agree? Minus alpha is same thing as plus alpha. Similarly, minus 1 is same thing as plus 1 in Z2. Alpha is not element of Z2, remember, but the coefficients are in Z2 only. So this thing is same thing as alpha plus 1. Okay? Do you understood or?
Yes.
Yeah. So similarly, so alpha cube is equal to 1. Now it looks like, so basically GF4 can be written as 0, 1 alpha, and 1 plus alpha, we can say it is alpha square, where alpha square plus alpha plus 1 is equal to 0. This is our condition, right? So this is a field. Now let me see if it is a field. So let me make a table here with respect to addition. 0, 1 alpha square, 0, 1 alpha square. So tell me one more thing. What about 2 alpha? What is the value of 2 alpha? 2 alpha. Any idea? Please unmute and answer. What is the what? 0. Why? Because this coefficient is 2, and coefficient is modulo 2. It is 0, right? Similarly, 2 alpha square is what? 0. 2 is equal to 0, right? That means alpha is equal to minus alpha square is equal to minus alpha square, 1 is equal to minus 1. Okay. So now if you add 0, 1 alpha square, 1 plus 1 is 0, 1 plus alpha is alpha square, 1 plus alpha square is alpha. 1 plus alpha is alpha square, alpha plus alpha 2 alpha is 0, alpha plus alpha square is equal to 1. Alpha square plus 0 is alpha square plus 1 is alpha square plus alpha is 1, alpha square plus alpha is 0. This is with respect to addition. Similarly, we can make a table for multiplication, right? 0, 1 alpha square, 0, 1 alpha square, 0, 0, 0, 0, 0, 0, 0, 1 alpha square, alpha square, alpha cube is 1. We just saw that alpha cube is 1 here, right? Alpha square into alpha is alpha square. Alpha square into alpha is alpha cube, which is 1. Alpha raised to power 4 is what?
Alpha.
Alpha. So we got it. So that means now you just check whether every element has a inverse here with respect to addition. Yes, because 1 plus 1 is equal to 0. Alpha plus alpha is equal to 0. So alpha is inverse of itself. Alpha square plus alpha square is equal to 0. So every element has a inverse with respect to itself with respect to addition. Now with respect to multiplication, we encircle 1 here, multiplicative identity, and we can see that 1 into 1 is 1. So 1 is self-invertive, right? Alpha into alpha square is equal to 1. So alpha and alpha square are inverse of each other, right? So every non-zero element has an inverse. So this is a field. Field with 4 number of elements. Okay. So now remember, this is a beautiful thing, because now don't confuse yourself, because alpha looks like alpha is a cube root of unity. Is that correct? Because alpha cube is equal to 1. It's a root of the unity, right? But actually, in the cube root of unity over reals and complex is different than this. Because now alpha square plus alpha plus 1 is equal to 0. I cannot, I'm not solving in the same manner as, we cannot apply Shridharacharya formula here. Okay? There is no real or complex numbers here. This is a different thing. So this is field with 4 number of elements. Any question at this point before I think we close? Any question at this point? Any question? Please unmute and answer and ask. So you understood it? Very nice. So I think that's all. Next class, we are going to show you certain ciphers, how to construct certain ciphers. I'll give you some idea about finite fields. I will give 5 minutes more introduction to this finite field in the next class, because this is sometime this is too much, so I think you need to think about it. And as a question, I'll say that can we construct field with 6 number of elements? T-time problem. Or what about 7 is fine, because integer modulo, we know that integer modulo n is a field if and only if n is a prime number, right? So 7 is a field. What about 8? Can I construct field with 8 number of elements? This is also an exercise. Please do let me know. I think this you have done last time, but please let me know if you're not able to do this. Okay. So this is also tea time problem. So I think you have to drink a lot of cup of tea today in order to enjoy the beauty of mathematics, right? So I guess that's all for today. Any question, then it's fine. Otherwise, we can close, right? Any question?
Sir, can you go one slide back?
Yes, sure.
So while considering, we always consider alpha plus or 1 plus alpha kind of thing here, or there is any other method even we can consider?
Oh,
So
where,
because you're
what do you mean by 1 plus alpha? Here you mean to say?
in field of 4, when constructing, this is a plus alpha b.
Yes, a plus alpha b, right?
So a and b are 0 and 1 in case of
right. I have done the analogy just like from real to complex, nothing more than that. You see,
Okay.
a plus ib, I have just taken a plus alpha b. That's all.
Okay.
Exact same analogy. Nothing, right? Everything is exactly same, right?
So, but when we go for higher fields, we will have more numbers.
Yeah, when we go for higher fields, so then we need to consider something like this: a plus b alpha plus c alpha square.
Okay.
Okay. So it goes like a polynomial kind of thing.
It's polynomial function. Fine.
Yeah. So
B
keep
plus
on.
alpha cube,
Yeah.
it will go then.
Right. Got it. So for example, for Z of 8, you need to consider A plus B alpha plus C alpha square, where A, B, C are in Z2, right? So one more thing is there. Before closing, these elements I can mention. So this GF4, one way of mentioning them is we have so A plus alpha B, right? Such that A and B are in Z2. This you can mention it like 0, 1, alpha, 1 plus alpha, right? This is one way. Another way could be 0, 1, alpha, alpha square. So this is polynomial representation. And this is power of alpha representation, right? Another one is from here, we can look at the coefficients of A and B. So 0, 0, right? 1, 0, 0, 1, 1, 1. So you can represent as 2 bits, 2-bit representation here, right? So now you see these 3 representations are useful. Sometimes we use this, sometimes we use this, sometimes we use this. So in actual practice, this is what is very, very common. And as you know that our bytes, the bytes that we look at in our data, bytes are nothing but members of field with 256 elements. Okay, 2 raised to power 8 bits here. Okay, so these are elements of field with 256 elements. So these are very, very important data structure, I would say, for the whole computer science. So so they all lie in finite field. That's why we can do all kind of operations. Okay. Any more question? You can unmute and tell me. You just interact with me, talk to me so that you can learn more. Right? Any more doubt? Any more question?
No, sir.
Okay.
No,
So
sir.
thank you and enjoy your weekend. We will see you on Monday, 12 o'clock, next class. Okay. Thank you very much for joining me. I will be issuing the first assignment, but actually it will be based on the next class more or less. Okay. And
So one more question. If we are not done your discrete class, so any prerequisite?
no, nothing. I have covered everything here. As you see,
Yeah,
I have covered
fine.
everything here.
Yeah.
No issue. I'm covering everything here. If you have done discrete math, because I have taught few things, so I'm trying to recall so that you are able to recall something. If you have not done it, it's fine, no problem. I'm covering everything here. No, every basic is covered here. Okay.
Yes, sir.
Okay. See you then in the next class. Thank you very much.
Thank you, sir.